翻译的对。 This is the parameter of discussion. We have the variables, that is the magnet mass, the string mass, the previous height, the magnet mass and height, and the magnet number. So we also have the dependent variables, the pendulum frequency, the phase, and the exponent. So let's look at our application video. So you can see the video actually travels in this path like 8 and so. Okay, so this is the series. So we actually use the function here to show you guys how the magnetic field actually is present. And this is the magnetic force between this space and the pendulum. And this is more about the modeling. Also, so we can see that it's actually is under unstable equilibrium when it has a middle, so it could be moving this way or moving that way. So the change is in the equilibrium state, and then chaos resonant state is here. The motion very different depending on the initial conditions. So this is the economic exponent. So it's used to analyze the motion scale. So this is the phenomenon analyzed. We got the xy in x1 and xy in x2. So we can see that the pendulum travels around the base, and there's two phases. Okay, so this is the high, the pendulum's height during the time, and xt. Okay, so the phase space. So the X is a double linear spiral according to the two attractors from both sides, since the magnet has two sides. And this is the right part of so you can see the center point is proved by the curve. And YC are single linear spirals as the two attachments exhibit same directions of forces. So we use the external exponent, and we can see that the slope here is the most significant slope is actually positive. So we can say that the liminal exponent is actually greater than this. So this is chaos movement, and we see the case over there. Okay, so we have the reversed. So it's transient chaos. So we can plot factors facing the boundaries. So we measure the force of the magnetism using this setup. So we have a ruler here. We measure the distance from this. This is actually a core, and we stick that we use the tape to put the magnet on this board. And we measure the distance between the board and the scale. So we can measure if the scale has the readings tell us how much the force is. Okay, so this is the experimental results. So we can use by looking at this graph, we can know that how the force will perform. Okay, so experiment one, we talk about the initial conditions and the pressure-based formula. We change the release point right here, and we fix it to other parameters. So actually, we just pull the pendulum right here, we release it, and let it go. So we'll see what's happening. So this is the video. Okay, so in the low energy form, we can see that this can actually pass this line. Since we get pulled back by this space right here. And in this one, we can see when you travel right here, and the energy actually increase, so you actually start in another side. This is fixed by the other side of the base. So observation. Okay, so these 2 points are the stable, and we will just forward. Okay, so this is the series. Okay, so we have the stretch of the phase space. So we can see just as the previous picture. Actually, it has a routine like a shape. Okay, so the phase space is smaller with less energy since it's, the place is passing is actually smaller since it can pass the middle line we just showed you this. Okay, so to analyze this better, we have a board right here, and we we spread the board into many pieces. So we can calculate how many times the pendulum actually passed those part of the board. So we can calculate the and you see that in this part of the board we can see it has more times when the pendulum pass through, and in this part it actually don't have any. So we can we can see that the XT graph will actually look like this, something like a sine graph, and this part of the graph actually happens very rapidly. And this is the FFT analyzed for the previous graph. So you can see two peaks, two main peaks are here, and multiple peaks here. So it's the length of the height of the pendulum change. Actually, when the height increases, actually it has more peaks, more main peaks on the FFT graph. So I can tell you that it's more peaks. This is the analyzed thing next to. So we can see there's more peaks appearing on the graph compared to the previous graph. Okay, so we can compare this experiment. So we can see there's 9 cm, 10 cm, and 11 cm. So we can see using the neutral frequency equation right here, we can actually compare it at different time. We got experiment 2, the transient actors, the magnetic distance. So we show you guys those pictures before. So we use this to actually tell you guys the equilibrium. The equilibrium in the previous. So we can see that this is a magnetic field and magnet. Okay, so we can see that this actually goes here and it stops right here. And in this one, actually just stuck in between the two bases. This is the simulation, so we can see that actually this is the. Okay, so look at those pictures shows you that the pendulum actually moves right here, and actually it won't stay in a stable. Okay, so this is the experimental setup. So we have the magnetic distance right there. So we change the distance between the two bases, the two magnetic bases. So we can see that how the magnetic field actually affect this motion. So this is the experiment. And you can see right here, actually when the distance between two bases increase, actually the pendulum do a little bit rotations in the region. So and this is the phase stretch. So you can see, and this is when the bases are closer, we actually pass the middle of the or more penny. So it's more distant. There's more dot than in the middle of the probe. And in those, we can see that actually the pendulum it passed the line between two bases and stuck in the outer side since the energy is lost and will get stuck by the magnetic field. And this is the discussion. This is the discussion of experiment 2. So we can see the number of transients, and you can see that actually you get look over here. So this part is kind of messy, and then we have the chaos. It's more chaos than trading and gravity. The movement can be classified into two phases. And the result of the pendulum is sensitive to the initial conditions, as we mentioned in the previous experiment. And the motion is classified as translated chaos with a positive Lyapunov exponent. And the initial energy shows the size of the phase space, the distance of the magnetic stress, the phase space horizontally, and the fracture base boundary is stable phase 2 under normal. And first, we'll have a quick summary right here. So first, we observe the motion and classify the phenomena into two phases due to the exposition. Second, we put the phase space and calculate the Lyapunov exponent right here, and it's positive. So we classify it into a chaos motion. Okay, so this is the reverse.
Question for the opponent.
Okay, you mentioned a lot on the Lyapunov exponent concept.
Okay, so the Lyapunov exponent is actually used to clarify if the motion is chaos or not. So here's when the Lyapunov exponent actually just
like when that number is bigger than 1, it's not.
we actually find in the graph we actually find the most significant slope, and if that slope is actually positive, we'll clarify it into a chaos movement.
Oh, okay. And also in page 28, how do you calculate the energy? Like you calculate by 828. Like you mentioned that is how many times you use that.
Oh, we use tracker to track the we use
Then the 31, what's the page?
Oh, this is the fast Fourier transfer. We actually
So what is the y coordinate?
it means this is the friction and this is the peak.
So x-axis is friction and y-axis is
Frequency and
frequency
and y is the power.
frequency and power.
Yeah.
What is power?
It means the power of the weight or weight. I think you can maybe consider into how significant the
Okay, I will mention it later. In page 33, what did you define it as a natural frequency?
So visual frequency actually.
Like why is this form?
We actually read this from the reference. So,
But I just say reference.
yeah, we actually have the reference.
Thank you.
Preparation for the opponent for 3 minutes.
This is the opponent speaking. I'm from team GGWP, and now I'm going to summarize what the producer says. So in the phenomenon part, he considered a chaotic system and he provided a rigorous provement about how did you prove that it is a chaotic system using the phenomenon exponent. And the theory they use is about the field and potential energy. And also they consider the dipole magnetic field. They also include that whether stable or unstable equilibrium is. And in the experiment, in the preliminary experiment, they measure the force of the magnets, and in experiment 1, they change the release point, and in experiment 2, they change the magnetic distance. So there are some pros and cons about the reporter's report. They provide a complete preliminary experiment, and the preliminary setup is easy to observe and control throughout. They also conducted a 3D simulation to prove they are right. But for the cons part, they lack some graph. So for some graphs, they lack some units and some coordinates. And they can also consider the magnets are repellable. So for the discussion part, I will be very curious about considering dipole moment, magnetic dipole moment in your series, yes or no. And in conclusion, in your conclusion, you say in low energy, like specifically how low. I'm really curious about. As for the phenomenon, in your experiment, you release it only with the horizontal, with the base magnet. So I'm curious about, did you observe or do if you release in a vertical direction? Is that going to be chaos? And in page 36, what's the initial condition and unit? And since you say it's chaos, so it means that it's highly sensitive to the initial conditions. So why don't you consider the Earth's magnetism? I'm curious about this too. As for the other part, like you say, it's chaos. So did you mean that you cannot determine that the magnets will be attracted to the left or the right, or you have any improvement to prove that? And what makes it stop? What makes this pendulum-like thing stop is a very worth to consider. And how is the magnet released in your experiment? Because you said that it's very sensitive to initial condition. So I'm going to invite the reporters to ask the questions. So I would like to know, in your theory, can you determine whether the pendulum line thing, the magnets will be attracted to that or right, or it's just going to be chaos? Has nothing to do with other parameters.
Actually, when a magnet passes, the pendulum passes the magnet, you actually get a track and cause the energy to decrease.
Cause the energy to decrease?
Yeah, if you put the pendulum right here, and without the base, the magnet base, you actually go like this. And so when it goes like this, then the base of the magnet base is pull it back. So it actually causes the energy to decrease.
Okay.
So the energy part, you mentioned that what is low energy and high energy.
Yeah, can you please send the conclusion page to in conclusion? Yeah, here. This what's like under low energy, like exactly what's the boundary condition? I'm curious about.
Oh, actually, I would say that what is the low energy means is when we release the pendulum, it actually has a potential energy, right? And so we actually compare the different the energy by different height we release. So we have a different potential energy.
Like different initial potential energy received.
Yeah.
And you release it at the little velocity is zero.
Yeah, we just put it in
You
a
have
certain
to
height.
release like with hand or something.
Yes.
You said it is sensitive to initial conditions, like it's chaos. So why can you use hand?
Well, we actually we don't do this by the machine, but we can actually use some tools like a chopstick or something. We just hold and we want to minimize the effect when we use it.
So I think you can maybe like you have done it in simulations that can decrease the deviations about when you release it. And about the next question, I would like to ask what makes the pendulum to eventually stop? And will this pendulum, like when attracting, is like strictly attracted or it is going to vibrate on the magnets?
Actually, I mentioned previously that when the magnet pull the pendulum backwards, it actually need the energy to decrease, right? So why it leads the pendulum to stop is actually by the pulling force produced by the magnet base.
No, I mean, can you, okay, let me rephrase it. Can you first define stop in this experiment? What do you mean by the magnet will stop?
Actually, so in the observation video, you can see that the pendulum actually moves in this way. And actually, when the energy decreases, the amplitude actually will decrease. So actually, you will move between the two bases and in this shape. So we will call it the vibration. And when the energy keep losing, actually the vibration will.
So this stop does not mean that it is static, right?
Yeah, it actually means static, but what I mean is after the vibration, actually the energy keep losing. So
let me make it more simplified. The stop here means that the velocity is 0 or not. Yes or no?
yes.
Yes or no?
Can you repeat it?
The stop here, what makes the pendulum eventually stop? When it stops, the velocity is 0 or no?
Yes.
It's 0. But in my opinion, I think that when we define the pendulum to stop, I think that it means that the kinetic energy of the magnets suspended on the string is not that it cannot overcome the potential energy caused by the magnets on the base. So it will eventually like vibrate on it and never goes out the control of the magnets on the base. You know what I mean?
Yeah, but
So I think that when we define stop here, we cannot define that the stop is the final velocity is 0, like you mentioned. Because actually it's going to vibrate on the top of the magnets. It's not going to be static. It's going to have some velocity, like vibrating on the magnet's output, not going to stop right there.
yeah, you won't just add a stop, but I was thinking it will raise actually came into a phase of equilibrium. And since the two bases are keep pulling this one, actually I mean when it's right here, actually the two sides of the force will stay the same. So I think it will eventually stop. But maybe we would have to wait for its vibration for a long time.
Okay. About the Earth's magnetism, did you consider it?
No, I think it's negligible.
But since it's sensitive to natural conditions?
But if we do the experiment in the same place, I think.
You think it is like the same?
Yeah.
But I think it will. Then did you calculate the order of magnitudes about the Earth's magnetism?
No, I
to
didn't.
compare it? Oh, I think you can do that to prove that this is negligible. And also in page like here, okay, I see that you only release it in the horizontal direction with the base magnets. Like if these two magnets is like this here, I haven't seen that you release like this direction. Did you consider this in your experiment?
No.
Can you predict it whether it will be chaotic or will eventually fix to left or right magnet?
If we put it right in the middle, I think the two sides of the pulling force will stay the same. So it makes it maybe you will do something like a SHM between the two spaces.
Oh, okay. In my opinion, I think that since it is like chaotic, like you said, so I think if we release it in this direction, when we reach here, this part where the potential energy gets stronger, I think here also we'll have a chaotic system where we cannot determine whether it goes left or right.
But if we release it in this case, actually we have two different magnets, and it pulls the pendulum in different directions, and the distance between the pendulum and two magnets are different. So I think that is the main reason why it's kept. pendulum right here in the middle. You just release it. I think if the two side, the force on two magnet base is quite the same, you won't need to the chaos motion. But you actually still cause the potential energy to decrease since when you pass through this, pass over the two bases right here, actually the two magnets will actually pull it back, so the energy will still decrease.
Okay, and I think that in the problem statement it said 1 or 2 magnets. Can you show me the 1 magnet one?
We don't do the one magnet one.
But the problem statement says 1 or 2, so you don't want to consider. You only consider 2 magnets, right?
I'll say that we just consider this.
2 magnets. Okay. And like in page 42.
Sorry. So the problem statement says
1 or 2. It's magnet. 1 or 2.
Yeah, it's 1 or 2.
So you only use 2.
Yeah, so I just
so it didn't come back to 1.
pick one.
Okay. And in page 42, I'm curious about what is trend science. I am not sure how to pronounce it. 42. 42.
So, you mean what is the transit?
Yeah. What is trend science? What's that?
It just maybe just imagine as a type of the chaotic motion.
Type of chaotic motion.
Yeah, we have different type of chaotic motion.
So in this type of chaotic motion, what conditions I have to gain so that I can get into this type of chaotic motion?
Actually, I was thinking that if this is sensitive enough to
No, I mean the initial conditions. Like you mentioned that there's different type of chaotic, right?
Yeah.
So in this type, what initial conditions should I fulfill in order to get into this, or is that just random?
Well, we just.
No, I mean.
Yeah,
You just need to answer the initial conditions that need to be fulfilled.
Well, I won't say. I can tell you like. Okay, so I don't know exactly why we get into this, but we can tell you that we are in the transition chaos by showing you the graph. So we can observe the graph.
So you only know the results, but you don't know what causes.
Yeah, we don't really know why.
Oh, okay. And back to the page 31 that I mentioned in the 2-minute short functions, like I still don't know what's about the existence.
Okay, so let me explain this.
31.
Okay, so
Yeah, first, please tell me what's the x-axis and y-axis crossing.
So the x-axis actually means the certain frequency.
Certain frequency.
Yeah.
Like
And
units is hertz.
yeah.
Oh, okay.
And this is actually the power. You can think it of how the intensity of okay. I'll change. Do you know the Maxwell the temperatures like this?
Oh.
Yeah, actually it means the similar way that when the peak temperature means like a lot of particles are at that part. So this actually means in the wave there's certain this.
Also, the y-axis is like intensity.
Yeah.
Oh, okay. Then
How
you're
much?
trying
Yeah.
Then you're trying to page 33. Like the definition of natural frequency, like what's that?
So
How
we
do
just
you get it? Thank you. So I'm now going to conclude what we have discussed before. So I asked the reporters about the definition of the pendulum stop, and the vibration keeps happening. In my opinion, the vibration will keep happening so that when it stops, it doesn't mean that the final velocity equals 0. And they use hands and chopsticks to stabilize, to minimize the initial deviation they have. But since it's chaotic, I don't think that is feasible. And as for you, I think that they need to precisely calculate the Earth's magnetism because it is chaotic, sensitive to the initial conditions. And about the natural frequency, they didn't give a derivation or how they derive it or what's that mean. The definition of natural frequency in the PPT is not sufficient. And what conditions are considered to get into this type of chaos? They didn't provide, they only know the results. Thank you.
the reviewer.
I have a question with the reporter. Can you go back to your slides on the FFT? Or at least maybe take your slides up. I just want to ask you what's your purpose of finding the FFT?
Oh, we have the previous.
Like what kind of mechanic are you trying to explore?
Oh, so that I'm trying to tell you that this is the main frequencies of the previous pictures. So we just want to analyze the frequency.
The frequency. Can you elaborate on frequency?
In this picture, we actually put this into the FFT to help to analyze the main frequencies.
Okay. I have a question. Another question to what the recorded data components. The reporter showed that the magnet seems to also slightly spin during the oscillation. Do you think this is significant? I asked
Oh yeah. Okay. So since the two bases, the two magnetic bases specific to the pendulum. So if it has a little torque relationship, actually the two sides of the force, the two bases are offering the pendulum is in different directions. So actually maybe to
So
turn
do you
back.
think that the different position in the field can also act exertion?
I think even though it's a small rotation, the force will actually make it into the equilibrium phase again. Since
What do you think?
I think I'm not sure whether it is significant or insignificant. So I think we can conduct an experiment about, like in this experiment, you use a string-based pendulum. Like I think maybe you can conduct a stick-based one. Like because if you use a stick one, the rotation of the outer magnets can be neglected. So we can compare these two and to see whether this is neglectable or not.
Okay.
but I think that is kind of it's not in the person one to kind of.
I think we move on to the next question. What other possible sources of energy loss do you think can occur to the pendulum during its oscillation? I offered you both sides.
Of course, the air friction, and maybe since we hang the pendulum with a string, the top of the string actually has the friction. So the friction of the string and the air resistance.
Okay, I agree with the reporters, but on top of that, I think that when the magnet tilts, that means that the tension force that connects to the magnet is not vertical to where vertical to the displacement, which means that the tension will be worse when the magnet is tilted.
Thank you for the shirt, for the.
I'll be reviewing magnetic cysts. This is the following statement, and the report decided to focus primarily on certain mechanisms of the pendulum in classifying different pendulum motions. They also decided to vary the relevant parameters such as the number of magnets on the base, the distance between the base magnets, and the base point. The reporters explained the phenomenon as the pendulum being at an unstable equilibrium, so that its initial conditions can influence its mechanics, such as transient motion and space mix. They created a three-dimensional model for the magnetic field, force, and the dipole. And they also claimed that the double phase space is reduced by the fact that there are two magnets on the base. For the experiment, they tracked the motion with different parameters and measured the magnetic field through a separate experiment, and also analyzed the data for phase space, the exponent, and frequency. The reporter gave a really comprehensive model and designed a setup that is designed for accuracy. They explored many of the mechanics and also gave a good simulation. However, I think that they did not address some possible some errors. Their graphs were sometimes unlabeled or unclear on what they were supposed to display. There could also be some better explanation in each concept, so the opponent could spend more time discussing other things. They could also have a more structured presentation to assist with this. And there were some other missing features that they could also have discussed. And there was also a significant lack of discussion of critical values, which is important in chaotic systems. And the reporter could have a clear voice. This is the opponent's discussion. They, in general, addressed many of the terms and they addressed the terms and methods of analysis during here by the reporter. They also discussed how the different analysis methods that can use to project the behavior. They also offer potential alternative methods that could improve the accuracy of the experiment or reveal something else. Some pros in the opponent's performance was that they questioned the user inside the reporter's experiment. They also attempt to provide different insightful approaches to how the theory of the experiment. However, I think they could have gone just a bit deeper into each of the arguments that they brought up, and they are still missing some sources of error. First of all, the sources of error that the opponent talked about was the release, which could have used a simulation to help support. The reporter said that it could indeed have used some more precise tools, and I did agree with the opponent. Okay. Yes, I agree with the opponent. The opponent also brought out how the equilibrium should be defined. They defined it as the point where the kinetic energy is less than the magnetic energy provided by phase magnets, while the reporter claimed it to be velocity zero, although the pendulum can still exhibit vibration. While I agree with the opponent, I don't think the reporter is entirely false, and I do agree that despite the equilibrium, it can still exhibit vibrations. So, but an important point of discussion that both sides of this is the point where the K would likely become insufficient. They also talked about what can lead to the equilibrium position. The opponent offered releasing the pendulum out of the plane between the two bases, while the reporter says that swinging it along the plane is critical to making it to exhibit the transient behavior, and I agree with the reporter. I think swinging it out of the plane is out of the scope of the topic. And finally, they also discussed and defined what the meaning of transients and how it can be predicted. The reporter is quite uncertain on why these behaviors are displayed, and I think it's important to explore these behaviors. Thank you.
Okay.
So here's my summary. And I want to clarify that since we have mentioned before that the friction between the string and the air resistance actually can cause the energy loss. So I think the pendulum will actually stop but not keep vibrating since we have the energy loss due to other factors except for the magnetic bases. And also, I agree with the opponent that we should measure the Earth's magnetism so we can make sure that this factor doesn't affect the result of our experiment. And I think that using tactics and certain tools to minimize the changes to the initial conditions is actually not that good, but since we don't have a typical machine, so we just maybe we can just use the model to predict it. But for the predict part, actually this is a chaos motion. So I don't think we can predict the what's happening after the initial conditions change. So I think predicting the motion is not we can do either with the zero. So this is
Okay, question number 30. Go ahead.
So first, I want to make sure that the data is at the top and the bottom opposite, and the opposite direction.
Means the interaction is attractive action.
Yeah. I mean, is attracting or pushing. Yeah.
Positive.
The closer your
Which one?
experiments, they are attractive. Yeah, I think it's attractive. No, I don't think it's attractive. Yeah, I don't think it's attractive. So shall we proceed? Yes, the closer one actually is the question, right? They are attractive or I think it's pushing. It's not attractive. So we have to say whatever. Most forward, most forward. It has the opposite force, so the same force of the push.
Now the problem asks they attract a magnetic suspension from the strip. Okay. Is there any question?
Slide 42.
Right. This one.
Yeah.
Right. So it seems that you have two phases of the motion, right?
Yes.
The beginning is steady, and then it enters the tension.
Yes.
And so do you think it's right that you perform the FFT analysis on both phases?
No, well, we actually separate the graph into two pieces, whether it's static or it's turning into.
So when you perform the FFT analysis, which phase did you
We
analyze?
should do both. Yeah, we separate the graph into two pieces and we do both.
No, no bad for your FFT.
Okay.
Like, I cannot know. Oh, so what are the new phase one? The steady phase?
This one is the local. Is it?
I don't know.
Bigger one.
The steady one. The steady phase.
So this is two pieces. In this phase is actually like this. And
The large one should have the lower.
this one is phase one and this is phase two. You see the differences from the XY graph.
Yeah, okay. It's not a good idea to use one and two. Okay, anyway. And then you perform simulation. So I'm curious whether your simulation agree with US
about the initial conditions with the theory running down.
But in the beginning, you have steady state, right?
Yeah, so
that's your simulation agree
Yeah,
with
but you
will become
cannot
steady phase.
yeah, but you cannot predict the whole motion.
I understand, but how about the steady phase?
I think yes, we can predict
Do you have result? Sure.
No, we don't have.
And then how do you know it works?
Well, since it's steady.
Okay.
No. Let's go to theory. Never mind. Okay, Jerry. For the reporter. Six, 477. For the reviewer, for the opponent. 77667. Okay. For the opponent again. 77677. For the reviewer, 66677.